classifications, or what do we need machine learning for?
Right, so thank you very much for the opportunity to speak here. So I will talk about classification program that we have been carrying out since 2003 of Z2 or Z2 orbifold. And so machine learning will appear, does appear here and will appear in the conclusions, but nowhere in between. So, what do we need machine learning for is maybe this is what I will try to demonstrate, right? So, so this work has been carried out since 2003 with various collaborators, and in particular, Glyn Harris, who was my student in Liverpool until last week. Well, he passed his Viva last week. So he was the one who was working on applying machine learning tools in our program, and he spoke in two of the meetings, or at least in one. He participated in two and spoke in the one in Munich, and unfortunately, courtesy of Steve Abel, he passed his Viva, and so he cannot be here. So I have to fill in for him. So. Right, so Ben Percival, who is my new student, second new student in Liverpool, he is sort of picking up from Glyn, and he might report next time on actual results from the machine learning that we're trying to do. So, and this work over there primarily has been done with John Withers, who is really the computer guru in our collaboration. So. And so I'll mention some related results obtained using this classification program, which spin of vector duality, exophobia, and string Z prime models. So string phenomenology, in some sense, is an answer in search of a question. One question, so the answer is the standard model, either the particle or the cosmological standard model, and its BSM extensions, or their BSM extension. And one question that one can ask is, what is a true string vacuum? Another question that one can ask is, can we identify a signature of classes of string compactification in the experimental part of the data? And I think given our understanding of string theory, maybe the second question makes more sense than the first. But as we make progress, we may refine our questions, right? So that's fine. So in this talk, I will describe the classification of fermionic Z2 orbifold compactifications, and what I want to try the message I try to pass on is what can novel, where can novel computational tools help? So at scales where we observe experimental data, the data indicates that the standard model is the right parameterization of all observable phenomena. And I think we can take the view. Some people have a different view. I mean, I welcome them to the view that the observation of the Higgs at 125 GeV indicates that the electroweak symmetry breaking mechanism is perturbative. At least this is consistent with being perturbative, and there's no real evidence that it should be non-perturbative. So taking that view, I think that it is, so it is it's reasonable to take the view that the standard model strongly hints to the realization of unification structures in nature. And my way of trying to sort of emphasize that is that the states of the standard model fits very nicely in 16 spinor representations of SO10. And if you, the gauge charges of the standard model states are experimental observable. They're not given by anybody, did not write them down a priori. So they are experimental observables. And if you count the number of experimental observables, you need to account for this number of gauge charges in the Star model, you have 3 generations, 3 group factors, and 6 states, including the random neutrino. So you need 54 parameters. If you embed it in SO10, this number of 54 parameters is reduced to 1, which is the number of 16 multiplets that you need to accommodate the Star model states. So this is an amazing coincidence that for me is the indication that the Star model begs to be unified. And there are additional evidence in the form of the logarithmic running of the Star model parameters, the gauge parameters, and we can see the matching or the compatibility with logarithmic running in the heavy sector Yukawa couplings, and proton stability, which indicates that we need a very high unification scale in order to suppress proton decay mediating operators, neutrino masses, and so forth. One experiment that I learned from Lenny Saskin many years ago is that this falls. So gravity exists. And the only way so if we want to really learn about the Star model parameters, given that that it is viable possibly all the way to the Planck scale, is by fusing a Star model with gravity. Otherwise we have complete freedom. We can add, quantum field theory are not constrained by any means, right? You build a model and it's constrained. But you have an infinite set and you're going to add infinite number of parameters which are continuous, so they're not constrained. And the only way to constrain is to fuse the Star model with gravity. And the only meaningful way that we know how to do that at present is by using string theory. So that's, for me, justifies doing string phenomenology, which to me is I don't know if the only game in town, but the best game in town, I would say. So the Premier League, with Liverpool on top. So, right. So the primary guide in trying to look for a string vacuum or a classical string vacuum is the existence of 3 generations and their embedding in SO10, which is a non-trivial constraint. So now, in order to reproduce that from string constructions, we know you have to use the perturbative rhetoric string because it is only the only string limit or the limit or the string theory that reproduces spinor representations of SO10 in the perturbative spectrum. So if you want to use a perturbative string limit to reproduce that picture, you have to use a rhetoric string, and you compactify it from. So since I assume that there will be also computer science people here, this is sort of introductory transparency to string construction. So you compactify the rhetoric string from 10D to 4D. The 6-dimensional compactifications are typically product of CT2 tori, for example, and you orbifold of this tori by modding out some internal symmetry of this space. For example, a Z2 orbifold of a circle gives you a segment with 2 fixed points. And the free fermionic model are just Z2 cos Z2 orbifolds of this 6-dimensional space. And the features that these models reproduce, which are phenomenologically attractive, is that they produce, and they were, from the early constructions, they reproduce the canonical gut embedding of the weak aperture, which was not trivial in the early sort of orbifold constructions. And the second argument, which you can say is heuristic, is that you're dividing a 6-dimensional space into factors of 2, and so you naturally reproduce, you have a natural way to reproduce 3 generations. So an answer to that question. So I think that was asked whether 3 generations are natural. So that gives you some natural framework. So the free fermionic models have been around since the late 80s, and they produce sort of a laboratory for the exploration of the Star model and its phenomenology and the phenomenology of unification. They produced the first minimal supersymmetric, so the first model that gave rise to the minimal supersymmetric standard model back in 1989. And I will refer to this as the FNY model. And then various phenomenological questions pertaining to the spectrum of the standard model were studied around the early 90s. And in more recent years, we've been looking at classification of large classes of vacuum in this context, in this framework. So there are many other approaches, and I think all are welcomed and all are well-deserved and should be pursued. And I think the aim at the end will be to try to isolate, or what are the signatures of, say, different classes. What are the particular signature of different classes, and different people should pursue their sort of favorite scheme. Right. Now, we know since around 1995 that the different string theory is just limits of a more fundamental theory. So one may ask, which one should we use? And I think the previous speaker actually sort of asked this question. And I think that one should not expect to fully characterize a two-string vacuum using one of those limits. So using any of those limits, you can probe some of the properties of the two-string vacuum, but not necessarily capture all of its properties. So, so for example, if you want if you take as your guiding principle the embedding of the star model in SO10 representation, then the limit that you can use is the theoretic E8 cross E8 if you want to use the perturbative limit. If you want to study dilaton stabilization, you have to move away from that limit, because we know that stabilization of the dilaton correspond to opening up another moduli. So if you want a finite value for this moduli, in the perturbative theoretic limit, it has a runaway, so it has a runaway behavior, and if you want to stabilize it, you have to move away from this perturbative limit. So different limits may capture different properties of the two-string vacuum. In my sort of this approach, the two-string vacuum will have some Z2 equals Z2 orbital characteristic, and you can probe different properties of this Z2 equals Z2 orbital in using different limits. Right. So just a bit on the general structure of the free fermionic construction. So in this formalism, you present, or you all the degrees of freedom that you need to cancel the conformal anomaly as free fermion propagating on the string world sheet. And you have 12 free fermions corresponding to the left-moving compactified coordinate and the right-moving compactified coordinate. And then you have 16 complex world sheet fermions. 3 of those produce 3U1 symmetries, and 5 produce the SO10 GAT symmetry, and 8 of those produce an hidden SO16 subgroups that can be enhanced to in 8. And models in this formalism are sort of represented in terms of boundary conditions basis vectors for the world sheet fermions, and the one loop phases in the partition function. Now, all these models correspond to Z2 equals Z2 orbifold with discrete Wilson lines. They are formulated at the free fermionic point, but the moduli that allow you to move away from the free fermionic point are in the spectrum. So they're just a different representation of Z2 equals Z2 orbifold. And more generally, they would correspond in a smooth limit. They would correspond to some K3 compactification with a T2 spectator and modded by an additional Z2. So the K3 modded by Z2 will produce orbifold of K3. So you can also explore a smooth limit of this class of models. Right, so the old school of the construction of the phonological vacua was using a fixed subset, which was called the Naes set, which was a set of 5 basis vectors. Out of those 3 will produce each one, so they correspond to the twisted sectors of the Z2 cos Z2 orbifold, and each one of them will produce one generation, and the n equal 4 space-time supersymmetry is broken to n equal 2 by one of these basis vectors, and then to n equal 1. And the gauge group at this stage is SO10 cross SO6 cube cross E8. And to go beyond this so-called Naes set, Naes is an acronym for Nanopoulos and Agony and Ellis, and in Hebrew it means pretty. So it's the pretty set. And to go beyond, so this was a common set for a large class of phonological models, and to go beyond, you add 3 basis vectors, e.g. those in the FNY model. Then the number of generations is reduced to 3, and the SO10 group is broken to one of its subgroups, for example, to the standard model subgroup, with the property that the weak hypercharge has the standard SO10 embedding, the canonical SO10 embedding, and the flavor symmetries are broken to U1 symmetries. Now, all these string constructions produce exotic matter, and the exotic matter arises due to the fact that we break the gauge symmetry by Wilson lines, by discrete Wilson lines, and it gives rise to represent states in the spectrum that don't respect the quantization rule of the underlying gut symmetry. So these are exotic states that can be, for example, they carry fractional electric charge, in which case they have to be supermassive, or they can be standard under the star models group, but carry fractional charge under some additional gauge, some additional U1 symmetry. So we studied this kind of state with Claudio Coriano and Sanyon Chang back in '96. And so these states will be, you have an additional U1, which is the combination of U1 B minus L and U1 T3R, and you have to break this U1 down to the star model. So provided that you can break the symmetry with states that have the standard charges of the SO10 symmetry, there will be a leftover discrete symmetry that will forbid the decay of this exotic state to the star model state. So this produce natural dark matter candidates, and in particular the singlet. So it can produce singlet states, singlets of the star model that carry fractional charge and then the extra U1, and can be natural dark matter candidate, provided that this is realized. So in this FNY model, this model contains only 3/16 of SO10, and there are no 16 bars. So there are no 16 bars, there's no NL bar. So there's no the conjugate of the right-hand neutrino, so you cannot use a standard SO10 representation to break this U1 symmetry. You are forced to use exotic. So you're forced to use exotic with fractional U1Z prime charge. So this means that you're not left with a discrete symmetry. So this doesn't realize sort of the idea that we had back in '96. So we didn't have a string model. We proposed, we had other kind of states, but this kind of so it didn't actually realize the mechanism that we.
The dark matter candidate has fractional Z prime charge.
That's right. Yes.
Not charge.
Yeah. It's natural charge under the extra U1.
Yes.
Yeah.
What's the breaking pattern? You had SO10, and now you have, so the U1 T3 this comes from Kani Salam, and U1 B minus R comes to break the SC5?
No. You break to the star model using Wilson lines, right? but you have an extra U1. In SO10, you have an extra U1. You have to break this extra U1 to the weak hypercharge. The extra...
Do you have a local picture where at some point you have...
I mean, this is the gauge symmetry that you have at the string level, right? You have an extra U1. You break SO10 to... SO10 has an extra U1, right? Which is a combination of B minus L and TCR, which you have to break. This is not broken by the Wilson line. This you break in the effective field theory. So the argument is that if you can break it using standard GATT representations, you'll be left with a discrete symmetry that forbids the decay of the exotic states to the standard model state. So this produces a natural stabilization mechanism. That's the argument, which otherwise you don't have really. I mean, that people talk about neutralino, but our parity is not not a reasonable symmetry within string or quantum gravity, because it's a global symmetry. So this didn't realize. So that's what I'm trying to push toward here, toward realizing this picture. So since around 2003, we have developed systematic methods to construct or to classify fermionic Z2 equals the two orbifolds. And in this method, we work with a fixed set of basis vectors, okay, and which at this level have an SO10 symmetry, okay, and then we add one basis vector that breaks SO10 to the Patisse-Lam subgroup, and one basis vector that breaks the SO10 symmetry to the flipped SU5 subgroup. And if you add the two basis vectors simultaneously, they will break the SO10 gauge symmetry to the star model subgroup. And the enumeration of the space of vacua is generated by this, so generating random sets of phases in the one-loop partition function. So in this, so we have a total of 66 independent coefficients in the partition function represented by these phases. So the phases above the diagonal, excluding this row, which is fixed to have space-time supersymmetry, are independent. So a priori, you have 2 to the 66 this independent string vacua, and they will have different phenomenological characteristics, different spectra, interactions, and so forth. So this is and in our method, you generate random choices of these phases. Right. Then we develop systematic methods to analyze the spectrum. So you generate all the twisted sectors in this way, and then you can define, so this sector will produce either 16 or 16 bar of SO10 with multiplicity 1, 0, minus 1, corresponding to 16 or 16 bar or null. And you can have a basis vector that or a vector that maps to a sector that produces the vectors of SO10. This we call the X map or the spin-off vector map. And you can construct projectors that will tell you whether each one of these sectors, the states from this sector, stays in the spectrum or not. And you can define similarly a chirality operator. So you can generate algebraic formulas that count the number of the net number of spinoids and their chirality and the net number of vectorials. And you can represent this in algebraic equations. So you can write a system of algebraic equations where the coefficients, the GSO coefficients are represented in terms of these matrices with these unknown coefficients. So you represent this GSO projection in this algebraic equation. You feed them into a computer, and you can count the number of solutions. So you can analyze the spectrum of each one of these configurations systematically, say, up to 10 to the 11 or 10 to the 12 configurations. So this is our classification method, and some results that we obtained from this method. So the first interesting result is with relation to spin of vector duality. So if you count, so this is, for example, you count the total number of spinors or anti-spinors, the total number of models with spinors, and the total number of models with anti-spinors, and the total number of models with one spinor and one anti-spinor. You add them all together. So this is a large number. It's around 1 billion. So you count the number, you add them together, and you find that it matches exactly the number of models with this number of vectors. So this led us to the to think that there is this duality between the exchange of the total number of spinors and anti-spinors and the total number of vectors, and it reflects a discrete symmetry under exchange of phases. This is a so-called spinor-vector duality, and this is another realization of it. So this is a density matrix that of the total number of spinors and anti-spinors versus the total number of vectors, and you can see that it is invariant under exchange of rows and columns. And you can understand this. You can understand where this duality is coming from when you consider the extension of the SO10 symmetry to E6. So in E6 you have the representation of 27, which decomposes under SO10 as 16 plus 10 plus a singlet, and the 27 bar decomposes under SO10 as a 16 bar plus 10 plus a singlet. So if you have an E6 symmetry and you count the total number of 16 plus 16 bar, it is equal to the total number of vectors. So E6 is self-dual under exchange of the total number of spinor and anti-spinor and the total number of vectors. When you break the symmetry to SO10, there is a remnant of this symmetry at the enhanced symmetry point, which is this spinor-vector duality. So, for example, one question for the machine learners is, can a machine discover this spinor-vector duality? Right. So this is a question for the machines. Another result that we have observed is the existence of exophobic string vectors, so with Ben Hassel, Kyriakos Christodoulides, Kostas Kounas, and John Rizos. So this is number of 3-generation models, so these are all 3-generation models, versus the total number of exotic multiplets. And you see here that there is a column with 0. So this means that there are 0 massless exotics in these models. There are massive exotics, so they have to be exotic state due to the theorem by Schelekens, but no fractionally charged states in the massless spectrum. Okay, so this was what we call exophobic string vacuum, so was also obtained using our sort of random generation or random classification method. And this is the example of the classification of the flipped SU5 class of models. And here what is observed is that there are no exophobic models with an odd number of generations. So my student, Hassan Sonmeh, who did this classification, didn't like this result. I liked it because it showed that you can extract finite properties of this large space of 10 to the 12 vacua. So by contrast to the exophobic model in the Petit-Salam case, you see that this is, to my mind, quite striking. I mean, the fact that you have zero exophobic vacua for odd number of generations, in this case, in this space of vacua. So that doesn't reflect anything more, but still, I think it's a distinct result. Right, so another, so I don't know if I'm getting pressed in time. Something like that, right. Okay, so another result was extracting Z prime model from the spectrum, from the space of vacua. And the difficulty with getting string-derived Z prime model is that either this U1 combination has to be broken at a high scale in order to generate light neutrino masses below, say, of the order 1 electron volt. So, and the other difficulty is that when you break E6, the U1 that typically people discuss in E6 string-inspired phenomenology is anomalous. So if you want to generate an anomaly-free U1, you have to do something. So what we did was so this is a configuration that produces a model where this combination, which is inside E6, is anomaly free. So we did that using our random, using a fishing algorithm. So we generate random choices of these matrices, and we found one configuration in which this U1 is anomaly free, essentially at the SO10 level, but it maintains so it is self-dual under the spin of vector duality at the SO10 level, and it maintains the self-duality under the spin of vector duality when you break the SO10 symmetry to the Petit-Salam subgroup. So the multiplets form complete E6 representation. So then there's no E6 symmetry. The E6 symmetry is broken, but the multiplets are in E6, full E6 representation. So the U1 is anomaly free. So it's another example of a result from our systematic classification method. So now let me get into the next stage, which was where we get into the need for machine learning, for example. So, and in this case, this is a classification of the standard-like models using random classification. And what you see, so this is the number of models of the order of 10 to the 11, and the number of three-generation models was very low. I mean, relatively low, and in particular, there were no third-generation models with heavy Higgs, like the one that I wanted to have, namely coming from the 16 bar, nor with light Higgs. So that was sort of no phenomenologically viable models, and the same was true. So we tried to increase the sample by breaking. So this is breaking the hidden sector into SO8 subgroups, and again the result is similar. So there's no standard model. There's no third-generation model with either light or heavy Higgs. So this was rather disappointing. So something needed, if you wanted to get something viable from this classification, something else needed to be done. So what we did is we adapted the methodology. So and the adaptation was that we identified some fertility conditions at the SO10 level. So before breaking the SO10 symmetry down to the star model subgroup, we identify some conditions that we call fertility conditions. These are conditions on the random phases such that they favor the emergence of three generations. Okay, so you restrict by this, identifying these fertility conditions to subset that are amenable to producing three generations. So this was this stage in the classification, and then around this fertile cores, we produce a complete standard like model classification by adding the phases corresponding to the basis vectors that breaks the SO10 symmetry down to the standard model subgroup. And so then we obtain about 10 to the 7 three-generation standard-like models with light and heavy string spectrum. So this is an example of the data. So it's a sample of about 10 to the 9 configuration. So this is fertile 3-generation standard model. And the one that I want to highlight here is this case, right, that has the conjugate of the right-hand neutrino. So this produced what we aimed for. So it's a 3-generation model with heavy Higgs in the standard GATT representation. So you can break the GATT symmetry using a standard, break the additional U1 symmetry using a standard GATT field. And so you're left with a discrete symmetry that forbids the decay of the exotics to the standard model state. So this was one at the end, realizes this mechanism in a string-derived construction.
Sorry, what are the fertility conditions?
Sorry?
What are the fertility conditions here that you mentioned?
The boundary conditions, or the free fermion boundary conditions?
No, the fertility condition that you use.
Right. So the fertility conditions are constraints on the one-loop phases in the partition function, the GSO coefficients. Okay. So these are the fertility conditions that you can that we identified by hand. So we identified that if we impose some constraints on these random matrices, then you are amenable to producing 3 generations. So and then you classify completely around. So you produce randomly these SO10 configurations that satisfy these constraints. And then around these cores, you can get, you span or you generate all the possible configurations, and you get an abundance of 3-generation models. Okay, these are the fertility conditions. So now, this is where we're at the moment. Glenn was working on trying to, so basically in terms of machine learning, as far as I understand, this is similar maybe to a Go, AlphaGo type configuration. You have discrete sets. For favorable discrete sets, you would give a cookie. For unfavorable discrete sets, you'll give them, you'll take away a cookie. So in terms of the machine learning procedure that Glenn was pursuing, unfortunately he had to graduate. In the UK, it's 4 years or they cut your head. So possibly by next meeting we'll have more concrete results to report. Right. So I argue that the data favors unification. Strings provides the arena to study this unification with gravity. Free fermionic models correspond to Z2 orbifold, and they produce a fertile crescent where life and civilization can progress. So we started from exemplary models in the form of the Nae-based constructions. We progressed to large classes in our random classification. And now we're at the stage where we have two large classes. So we need some new tools to explore these 2 large classes. So the question is, can machine learning tool be used to identify fertility conditions? So Glenn was working on it. Now he's looking to apply machine learning tools in the stock market. And Ben Percival is continuing along this program, and as well as John Withers. So thank you very much.
Questions? Thank you very much.